Really? Like, how to prove that it's all grades. The only one I have is
oh, yeah, because it asks for subdivision because it's subdivision BJT.
And it doesn't specify that, it just says please prove that you have.
No, I think that you're just please prove that's operating ability you expect to be operating and it's operating system.
And then it just actually asks for that for the last. When I did the current drilling,
I couldn't even know. I picked it up.
I use the oscilloscope, so I essentially just turned it on, and immediately turned it off, and then turned power. I was just like, that's like, I didn't know how to stabilize. I was giving a story forward to my,
Okay, it's about time to start, so anybody got any questions about any of the homework that was due today or any other time, or any questions in general? I always try to do that at the beginning of class, because I figure if you got a question, probably other people have the same question. Anything? Don't do the homework? Nothing? Good. Nothing? Okay. Well, we went through chapter 6, 7, 8, and part of 9, and we got a test coming up. So, one of the things I'll tell you is I'll provide a formula sheet with only a few formulas. You'll get the impedance. I'll just show you the formula I always give you. And this is for the transmission line, but also for the waveguide you can adapt to. And that is the input impedance of a transmission line or a waveguide with a characteristic impedance Z0 and a load ZL and a link L. So we've talked about this. This is well known. I'm sorry.
The denominator is ZL and Z0 are not supposed to be flipped.
Oh, sorry. You're right. This is Z0 and this is Z0. My mistake here. You're absolutely right. It always goes Z0, Z0, Z0. I stopped. Yeah. Z0, Z0, that's right. And I'm sorry about that. I gave you that. Alright, I'll give you that. Now, if it's a waveguide, you have to calculate the characteristic impedance of the waveguide. And also, then you also have to have beta of the guide, which is different than just 2 pi over lambda. You all follow me on this? So look, that's the change with waveguides. But we use this for waveguide impedances. I'll give you that formula. For the half-wave dipole, if there's going to be a half-wave dipole, I'll give you the gain formula. And again, I'm trying to give you an idea of the things I'll provide for you. So if for a half-wave dipole, I won't give you the short dipole, but if it's exactly a half-wave dipole, and you have a current I, then I know that the electric field at an angle theta and distance r, E itself for this one is equal to J, and then it's simply 60 over R times E to the minus J beta R, and then it's going to be the cosine of pi over 2 times cosine of theta over the sine of theta. Now, the largest value that this angular function has, that's the f of theta, really the square root of inverse f of theta, because this is used for the power term. But the largest value it has is 1, and it occurs at 90 degrees. It's very similar to the sine of theta. Do y'all follow me, class? That's, that one I'll provide you with. And I'll give you the gain of a half wave, which is 1.64, or really directivity, but directivity and gain are pretty much interchangeable. And then it's going to be times the cosine of pi over 2 cosine of theta over the sine of theta squared. All right, so that would be the directivity. Now, I won't give you information about the short dipole, but any kind of loop I would provide you information for gain, or really for the H field or E field from a small loop. But what do we know about the small loop and the short dipole? Anyway, same gain, right? Right? The same exact gain, 1.5 times the sine squared of theta. And again, if it's this is a half-wave dipole. If it's a short dipole, right, if all of a sudden L here is much less, or is less than lambda over 10, and this is I naught on it, then, and this is the angle theta, I know that the electric field, right here, the electric field would be equal to, this is, I don't put this in here, but it's the A theta direction. Dipoles pointing in the Z direction. Electric field is J eta beta I times L over 4 pi R. It's times E to the minus J beta R, right? And then it's going to be times the sine of theta. And since this is short dipole over here, the directivity of a short dipole is just 1.5 times the sine squared of theta. Now, these two, the directivities, are nearly the same. If you actually plot them one on top of another, you'll see very little difference. But what's the big difference with a half-wave dipole compared to a short dipole? The radiation resistance, right? The radiation resistance for a short dipole is very low. For a half-wave, it's 73. We might as well talk about this right now. If we look at impedances, all right, for this antenna right here, V half-wave, Z in is equal to 73.2 plus J 42.5 ohms. For this one, Z in, and this is really, I better call this R rad. It's not really Z in totally, but it's the radiation resistance. So for over here, the radiation resistance of this is equal to what? It's equal to 80, right? Pi squared, and it's going to be the length L over lambda squared in ohms. Y'all follow me on that? Everybody with me? You'll need to know that one. I don't provide it here.
And then for the half-wave, if you knock that down to 1.
You're ahead of me, yeah. So, what Zach's getting at is that this half-wave dipole, it's true, but in the real world, without changing that gain or the E field, they'll be just about the same, within probably 0.01% or better. If you shorten that to be 0.485 lambda in length, then you get rid of the J 42.5. You get rid of that reactance. Y'all follow me? What's the benefit of that back here? Somebody else. Why would you want to get rid of the reactance? That J something. Anyway. John, take a shot at it. What does that do? What does it do for a given voltage? The more reactance, the less current, right? You would like the most possible current with the least possible voltage, right? That means we'd like to get rid of this J 42.5. We don't want that there, because it limits the current. Y'all follow me? We have to have a higher voltage to get the same current. Another way to do it, and this is not a good way, but another way to do it is just put a capacitor in series with that would have the same reactance, only minus J 42.5. That would get rid of it too. Y'all follow me? There's two ways. That's an additional element, and in the real world, you never add anything you don't absolutely have to. You try to minimize costs, and the more components you have, the more problems, the more things that can go wrong. So you try not to use a lot of components if you don't have to, especially in high power stuff, because then you get a lot of failures from heating. All right, so with me so far? So here's what I'd like to do today, unless somebody has a question. I'd like to talk about chapter 6 a little bit, because we haven't touched that in a while, and that quiz a lot of people had trouble with. And then after that, I would like to talk about a couple of problems with antennas, because we can cover the whole gamut. We can go from just we can use the Friese equation, we can do radar fairly quickly, as long as we understand the theory behind the operation of the antenna. And then, maybe a waveguide problem, and maybe some EMC. But anything else you want me to talk about, I'll be happy to. All right? Now this kind of covers the whole spectrum, but I want to start back in chapter 6. Now, y'all remember chapter 6 was where we developed the wave equation, right? We started, I don't think I need to go that far back. I'm not going to ask you to do that. If you had a physics course, they may, but I don't do that. This is an applications course, so we're taking a lot of the theory and applying it to the practical elements like antennas and waveguides, wires and things like this. So in chapter 6, so in chapter 6, in general, it's plane waves propagating in free space. So, and somebody from the back, what is a plane wave? What's the sort of the definition of a plane wave? Think about it. In your own words. There's no wrong answer here. Either you're very shy. Now, I know you guys know this. Remember the thing when I talked about dropping a pebble in a puddle and watching the actual really the waves, the ripples move out. Finally, you get to a point where there's just about no curvature, right? It's like a straight line out there, right? That's analogous to what a plane wave is. It's so far from the source of the electromagnetic wave that nothing really is changing. It looks like a plane wave, right? There is no curvature to worry about. Does that make sense to everybody? So that's what we mean when we talk about plane waves, we're talking about that. So for plane waves in general, you start with Maxwell's equations, you get down to this kind of an equation, right? And then it's going to be minus, really, gamma squared E equals 0. Do you all remember that? And here, gamma is what? It's equal to alpha plus J beta, right? And that's equal to the square root. Now, this you'll have to know. I'm not going to give you this right. This is going to be equal to J omega mu times sigma plus J omega epsilon, right? That's the general form. Do y'all follow me on that? And in general, when you have a wave propagating in free space, or propagating a long way from the source, you also have an intrinsic impedance, and that's equal to the square root of J omega mu over sigma plus J omega epsilon, right? Those are true. You all agree with that? Right? I'm just putting down the basics that you should know fairly well. This lends itself to the solution. If we talk about wave propagation in the z direction, and we have an electric field in the x direction that's propagating this way, in general, the electric field is given by some magnitude, right? E, the minus, and here it would be gamma z. This is the normal way to do it, in the ax direction. And there would be an H field also, and this is for forward propagation, so it's plus z propagation. That would be equal to E naught over eta, right? That eta, times e to the minus gamma z in the AY direction. Do y'all remember this? I mean, the units of the E field is volts per meter, and this is amps per meter. Really? That has a magnitude and a phase possible, right? So the normal way we talk about this is gonna be some E naught, right, over the magnitude of eta, and then the phase angle here would be e to the plus j, angle associated with that, but when we take it upstairs, it becomes e to the minus j, and you can just call it the phase angle associated with eta here, and then it's times e to the minus alpha. Oh, I should have said gamma, my bad. Gamma right there. E to the minus, then I'll break this out. Gamma z times e to the minus j beta z in the AY direction, amps per meter. Let me tell you what, I wanted to leave it as gamma there, but gamma is alpha plus j beta. When you do that, you get this, right? Now you can group what? Those two terms with the j's in front of it. You all agree with that, class? So you can group it, but that's the E field and H field from that, propagate. Now in general, when you have propagation, this is the way it's always written for a wave. If you have a wave, and I'm going to use an E field, the E naught is nothing more than the magnitude. It has nothing to do with the direction, it has nothing to do with the polarization. Do y'all follow? After that, you're going to get a term, and let's assume it's losses for now. You're going to get E to the either plus or minus, but I'm going to use minus j, beta, and then some direction. Now, if I had x, it would be going in a positive x direction, right? You all with me on this? If it was e to the minus j beta y, it would be going in the positive y. E to the minus j beta z positive z. If it is e to the plus j beta x, it's going in the minus x direction. Do you all follow? Remember that quiz where I gave those things and a lot of people stumbled around on that? How many remember that? All right. Now, I'm not saying it's your fault. Maybe I didn't emphasize it enough, but I want to make sure I get it clear. You have to know how to get the direction. Then the polarization will be this. So this is polarized in the y direction. Do y'all follow me? I want to make sure, because we're going to use those two little tricks. Where how to get E from H and H from E for a plane wave. I'm going to write them down, but I want to use this one, because this is the one we had problems with, if you remember. So if I take a look at this, I know that there's two things that are true. If I have the E field and I want the H field, now this is phase, it's what? It's 1 over eta, right? A unit vector in the direction of propagation crossed into the E field would be eta. Do y'all remember that? And if you wanted E, it's what? Minus eta, right? Unit vector in the direction of propagation crossed into H, right? I'm going to remember that, at least. Now, you have to know that. This is something you should be fairly familiar with. So, the way I get this, if ever you're confused, use the right-hand rule. Take your index finger, put it in the direction of E. E crossed H is the direction of propagation. It'll always work. All right, no matter, I'm wondering about that. I'm unsure, I'm tired. Just remember the right-hand rule, you can always pull it out from there. So, based on this E field, what is my H field? First, let's do it this way. For this E field, nobody in the front answers. What is the direction of propagation we just talked about? Somebody in the back. What, say it again? How many say it's positive X? Right? So this is positive X. Or AX, right? Now after that, I go over here and I do this, and I say, and I say that H here would be equal to 1 over eta. You can call it free space now. So it's just going to be values free space. Then it's unit vector in the direction of propagation, which is AX, right? Crossed into the E field. This is the E field. E naught, E to the minus J, beta Y, AY. Y'all follow me? You got to put down the whole expression. I'm going to ask you something about this, because that was the quiz you really, a lot of people stumbled on. And I feel it's more my fault than yours in a sense. I didn't push this hard enough. So now, what is the H field for this one? Well, in magnitude, it will be what? Just E naught over eta naught. Y'all agree with that? Now, this E to the minus J, because I made a loss, so it's beta y is gonna just stay there, it's gonna do nothing. What happens when ax crossed ay is az? So that would be the H field, that would be an amps per meter.
Should that be beta X, not beta Y?
I'm sorry, what?
Should that be beta X, not beta Y?
Beta, sorry. My bad. I'm sorry about that. All right, now when you get this right here, are you with me on this, everyone? I'm using this example. Next thing I might ask, likely, is the power density. What is the power density gonna be? Nobody in the front. I'm not just singling you out, but she's really loud at me. Anybody, go ahead.
1/2 E0 squared.
Right. Equals one, and this is what? This, in general, what is it? It's 1/2 the real part, right, of E cross H conjugated. That would be for what? That would be for a lossy media, correct, class? And in general, this one breaks down to what? And I'm gonna put it up here. It would be 1/2 magnitude of the E field squared over the magnitude of eta. Then you would have e to the minus 2 alpha z. Then it's going to be times the cosine of the angle associated with eta. And it would be, in this case, in the direction of propagation, which is ax. And that would be watts per meter squared. Now that's if it's lossy. I'm putting this down just to be sure I cover this base. You all agree with that? Remember that? How we did that? You can take 1/2 the real, E cross H conjugate, take the real part of that. Now, for this one, over here, if it's lossless, then the power density becomes simply 1/2 magnitude of the E field squared over eta, and it would be in the direction of propagation, AX direction. This would be watts per meter squared. And that's it in a nutshell. Do you all agree with that, class? With me on this? So now we've covered, I'm going to just ask one last thing. Just think about it, don't answer. Suppose, just to make sure, if I gave you something like this, you wouldn't be shocked. So I'm going to assume it's a plane wave, and I'm going to assume it's lossless as well. And I'm going to give you an H field here, and it's going to be 2 times e to the minus j, or plus j, 5y in the AZ direction, amps per meter. Alright? Y'all with me? It's a phasor form, it's a plane wave. So now I want the E field. Please don't answer, just think about it. What would you do to get the E field? Well, the first thing is you have to find the direction of propagation. You all agree with that? Let's do this, let's say it's in air as well. So eta is just eta naught, or it's 125. So let's do it that way. So I need the direction of propagation. Alright, how many feel it's in the positive y direction? How many feel it's in the minus y direction? Right, I think I'm getting to it. So this is going to be minus a1. That's the first thing. Now, next thing I do is what? I go over there, and I see it's minus eta, so it'll be minus 120 pi ohms, right? Times, and take a look at that, the direction of propagation, which is minus ay here, right? And then, after that, what do? I take that, and I'm over there, and I cross it into the H field, right? Cross it into the H field, or 2 e to the j 5y, and this will be in volts per meter. So what does that come out to? If you take one look at this, you notice the negative signs get rid of themselves, right? So that you don't have to worry about that. So now I have 2 times 120 pi. Y'all with me? And what is that? 240 pi, right? Then I have e to the plus j 5y, right? And then I have ay, I didn't put it up here, az over here. I have ay cross az, which is AX, right? And that would be volts per meter. I'm just showing you the kind of problem I could give you, and I'm making sure you're not gonna stumble on. You know how to get the direction, right? You know how to get the E field from H from E, because you can find the direction of propagation. What would the power density be if it's lossless and in free space? 1/2 magnitude of the E field, right? Magnitude of 240 pi squared, right? Divided by 8 or divided by 125, right? And it's going to be what? In the AY direction, right? Or sorry, minus AY direction. And it's watts per meter squared. Y'all follow me on this? That's the entirety of it. I want to make sure I cover this. So you know.
Can you explain the direction of the average power vector?
Well, the negative sign denotes it's going in the opposite direction. You can't have negative power. So you could actually do it by arrows. Personally, this is the way I would rather see it. Have it like that. I mean, just have it like this and have something like in the AY direction that way. It's going back. Because negative in front of that, it sounds like it's negative power. You can't have negative power. The negative sign only denotes the direction of power. That's it.
So for that one over there, what's the direction of that?
See, it's positive AX, right? So the power has to flow in the AX direction. Whichever way the fields are propagating, that's the way the power is flowing. Always. Okay? Fair enough? All right. That kind of gets through my concerns about that chapter. I got one other thing too. Let me use that as the example. So we're always going to, if I have this is the H field, this is the E field, you get the power density. All right, what if I ask for things like the frequency? Remember I asked this and the wavelength. So how do we get these? All right. Well, it's lossless, right? You can do it this way. Beta is equal to omega times square root of mu epsilon. That's true if it's lossless. Do you all agree with that, everyone? If it's lossless, that's true. This would be equal to what? Omega over C if it's free space, because 1 over square root of mu epsilon is C. Do you all agree with that? And that's beta. Well, beta for this problem is what? By looking. Class? Can y'all see in the background? What is it? Yeah, 5. Sure. So this is 5. So that means 5 times C is omega. 5 times C. And omega is 2 pi F, right? And therefore F is 5C over 2 pi. This is one way to do it. Do y'all follow? Normally, I mean, that will get you there. Everybody follow me on this? That would get you the frequency. How do I get the wavelength? And we could do this. What is it? 5 times C over 2 pi. I don't know what that is. We don't have to do it. I'm just kind of curious. 5 times 3 times 10 to the 8, that's 15 times 10 to the 8th over 2. 7.5 times 10 to the 8th divided by pi, whatever that is. I think it's a megahertz, maybe. Something like that. 200 megahertz.
Yeah, so 238.7 megahertz.
Alright, now wavelength, how do you get wavelength? Normally you say beta times the wavelength is 2 pi, right? And then 2 pi over beta would be the wavelength. Do you all agree with that? But if it's free space, it's just what? C over F. Isn't it, class? So for this one, it would be, because it is free space, C over F. And this is something just keep in the back of your mind. Wavelength is inversely proportional to frequency. The higher the frequency, the shorter the wavelength. That's it. And you know, you can never go wrong by saying wavelength times beta is equal to 2 pi, and therefore wavelength is 2 pi over beta. That will always get you there. Even in lossy conditions, it doesn't matter. That works all the time. Agreed, class? Now, are you familiar with, we did talk a little bit about shielding and stuff, but you know, when, you have a good conductor, all of a sudden, things change in a big way, right? One is there's skin depth effects, correct, class? You have to worry about, does everybody follow me on this, what skin depth is? There's skin depth, the velocity of propagation slows way down, and the impedance, intrinsic impedance becomes very small, right? So I want to just mention for a good conductor some of the things you have to consider, because we've been there, but we haven't really done much with this in a while. Okay. So, if we have a good conductor, what does that mean to you? I mean, if you had to explain this to somebody, what is a good conductor? There's one fundamental definition, right? And it has to do with the frequency you're at. It's when sigma is much, much greater than omega epsilon. Sigma is proportional to the current density of real current, electrons moving through something, not being stationary. This has to do with something called displacement current density, right? So this is the definition of a good conductor for a given frequency. And at that point, what happens? Then if you look at the intrinsic impedance, which is the square root of J omega mu over sigma plus J omega epsilon. I did this last time, I believe. I put this up here and I showed you. What do we do at that point? If it is a good conductor, and we have to compare omega epsilon to sigma, right? Assume sigma is at least 10 times, maybe 100, 200, 1,000 times bigger than omega epsilon. What does this approximate as, class? Just get rid of that J omega, right? J omega epsilon. And this becomes simply the square root of omega times mu over sigma, and it would be e to the j pi over 4 radians or 45 degrees. Do you all agree with that? Okay. Now, next thing is gamma, which is alpha plus j beta. I think I put this down in this class last time, but I'm teaching the same stuff over in my EMC course right at this time, so sometimes I'm not sure if I did it here or not. Do you all remember this right here? We just put it up too. All right, so what is this? This is equal to square root of j omega mu times sigma plus j omega epsilon, right? And what do we do here? This we ignore, right? We ignore that because we're assuming it's a good conductor. Now we get the square root of j. Didn't I put that up here too? Square root of j is 1 plus j over the square root of 2. Correct, class? Once we gather the terms, we find out this thing can be rendered as simply square root of pi f mu sigma times 1 plus j. Okay? And that means, for a good conductor, alpha is equal to beta is equal to square root of pi f mu sigma. Now that's very important, because what else, whenever you see a square root of pi f mu sigma as an electrical engineer, you should be thinking about one thing. That reminds me of something called skin depth, right? This is exactly 1 over the skin depth. Exactly. And skin depth, therefore, is 1. 1 over the square root of pi f mu sigma. And I'm just putting it here so you at least will have an appreciation for the reasons why I'm doing this. Here's the formulas. The reason I'm doing this is to bring it to your attention so you don't make silly mistakes on the exam. Now, when you have this, if you ever see an equation and it has the real and imaginary parts of the exponential argument the same times z, you know right away it's a good conductor. Y'all follow me? Anytime alpha and beta are the same, it is a good conductor, and from there you can proceed, assuming that, and it makes life a lot easier. All right, now that's true for these things. Now what about, since this is beta right here, right? Beta is just square root of pi f mu sigma. What's the wavelength? And on that one. And the velocity. Why don't we get velocity to phase velocity? So how do we get, you remember what I said a little bit ago about wavelength? What's the cardinal way to get it? The best way? Beta times the wavelength. That's the argument of the cosine is equal to 2 pi. And And therefore, lambda, or the wavelength, is 2 pi over beta. Now, that means it's 2 pi over the square root of pi f mu sigma. You can play with this, you can get it in a couple different forms. You can, basically get rid of the top pi, or actually make the top pi square root of pi. You can do all sorts of stuff with this, but this is fundamentally it. Now this wavelength always works, always works. How do I get the velocity, phase velocity? We had a discussion about this. You came to see me about group velocity. So how do you get phase velocity? Well, y'all remember it's omega, right? Divided by beta. You remember where I got that? Just to refresh your memories. Remember in the equations for the electromagnetic propagation, you get this kind of effect. Times cosine of omega t minus beta z ax. And I'm just writing this down to refresh your memory. Y'all remember that's the general form of the time domain, right? The argument of this is an angle. This is some angles. And if you take the derivative of the phase with respect to time, you don't want that to change. That is the phase velocity. You want to see how fast that phase point moves through space. When you do this, you get simply what? Omega minus beta times dz dt equals 0, and that means dz dt is equal to omega over beta, and dz dt is the phase velocity. That's how fast the phase is moving. Now for group, it's a little different. But the group velocity is the velocity of energy propagation. The phase velocity, and anytime you have a plane wave, phase and group are the same. That's the truth. Right? But in waveguides, that's not true, and we talked about that. So that's phase velocity. Do y'all remember doing that? So for phase velocity, here's where it gets weird. So omega is 2 pi f, right? And then we put down beta, and beta is square root of pi f mu sigma. Now we can go ahead and put square root of f on top, and we can put square root of pi on top, and make that 2, a 4, and put mu sigma on the bottom. We can do a bunch of stuff to modify that into a form you like. But the one thing that happens on this, and I just want you to look at this, because this is going to be square root of 4 pi f over mu sigma, right? Isn't that right, class? Well, what's the phase velocity when frequency is approaching 0? It's 0, isn't it? All right, just something to keep in mind. There's a lot of weird things that happen. Now, phase velocity almost loses meaning at a certain point. All right, really group velocity would be the way we talk about this in a physics class. But that's something to consider. Let's see, next. I think I'm about done. Polarization, we talked about polarization, right hand, left hand. The big deal is what? With polarization, if you send out a right hand circular polarized wave and hits a conductor, it comes back left hand circular polarized. So,
Did you go over how to tell if it's right or left hand?
anybody want to tell him when I erase the ball? You got a right hand? All right, put your thumb in the direction of propagation. If your finger lines this way, right hand, right? If it's going the opposite way, it's left hand. So it's like, this is direction of propagation, this is the E field. If the E field is rotating this way as you increase time at a given point Z, that's right hand. If it's going the opposite way, it's left hand. But I'm not going to focus, if you really want to know the truth, I don't play games about that. I'm not going to give you some crazy mathematical formula where you're going to increment to see how the tip of that thing's moving. I think the homework problems I give you, they're sufficiently deep. If you can do them without a problem, you're okay. And I don't think they're very hard. It's just graphing the tip of the vector at different points in time. Like just let omega t equals 0, 45 degrees, 90 degrees, and see how the tip moves. Then you can figure out left hand or right hand. You all with me, class? Okay, so, next. Review. I'm not going to ask you anything about fiber optics. You know, I think, I don't think I've ever, maybe I did, I don't remember ever asking about that. Not in this course, sure, in some of the other courses I taught, but not this one. All right, then we had oblique incidence. Now, I'm not gonna ask you anything about oblique incidence. I'm just telling you that because, frankly, the time you'd spend calculating some of these coefficients would be a little much. But you do have to know how to get that impedance calculation I showed at the beginning of class quickly and efficiently. Remember, that was one that really had people, you might say, using a lot of time on some of the quizzes I gave. They had tough time. So make sure you can do it efficiently. Watch out and make sure when you take the tangent of beta L, it's in radians. Do you hear me on that? Not degrees. That's a big mistake. All right, because beta is really radians per meter. L is in meters. So be careful about that. Okay. Now we have reflection. I didn't get through this, but I'm going to do it real quick. We'll finish up right here and then move into the waveguide. So when you have a media, and we'll just call this media 1 and media 2. Matter of fact, let me make this air, because that's usually the way it is. And you have a wave propagating in here, some E0 incident. You know you're going to get a reflected wave, right? And you're going to get a transmitted wave. E0 reflected. And if this has some value of eta 1, and it could be lossy, but for now we're going to assume this is lossless. And I want to know, now this is a classic problem that I give, form of in almost every EMAG test, first test, almost, so just hear me. Now this could be lossy, but if this is the case where I give you, this is eta 1, this is eta 0, and I can even give you the frequency of operation, but it doesn't matter if you have it or not for most of this stuff. All right, now, can you follow me on this or not? I could give you, hear me on this. I could write the mathematical form of this. I could have E0 like 5 e to the minus j 30 z, all right, in the ax direction. I could have that z. So to basically fold into Wentworth's book's coordinate system. I could do that. But if I asked you for the transmitted and reflected electric field and magnetic field, you should be able to get it, because there's two things you need to do. No, the reflection coefficient is eta, in this case I call it eta 1 minus eta 0 over eta 1 plus eta 0. The transmission coefficient is 1 plus the reflection coefficient, or it's 2 times eta 1 over eta 1 plus eta 0, right? That's the case. Now, once you have those, you know that the transmitted field's magnitude here is just the transmission coefficient, right, times E0 incident. And here, the reflected field is simply the reflection coefficient in magnitude times the incident field. You all follow me on that, class? Now, if we wanted the H field here, what would the H field reflected be? It would be what? The E field that's reflected, right? Divided by, in magnitude, I'm just worried about magnitude, divided by eta 0 here. Y'all agree with that? That's just the magnitude I'm showing you. The direction is obviously going the opposite direction. Over here, there's where mistakes are made. The H field is going to be that, right? But now it's over eta 1, right? Now it's over the impedance of that medium. It's different. Y'all with me? Now, y'all know that the incident power here is going to be the incident power minus the reflected power density part is the transmitted power density. Do you follow me on this, class? Can you all get the incident power density? What would that be? Not the usual suspect, somebody else. How about you? Yeah.
Okay.
I'm only doing this because he knows me, and we've had a class together. He's a very bright kid, so I'm going to give him some trouble. Anyway.
This is incident.
Yeah. 1/2.
E0 incident squared over eta 0.
Eta 0. It would be in watts per meter squared, right? Okay? Now, if I want the transmitted power density, Alright, how about Ben, you're back there, I see you in the gym all the time, what's the transmitted power density? It's the same form, 1/2 E squared over eta, right? Alright, so it's gonna be 1/2, my E over here is what? Now it's the transmission coefficient times E naught incident squared over, this is eta 1. Right, it's important, because I always see the eta values get messed up. They will use the wrong value. And that would be in watts per meter squared. Finally, how would I get the reflected power density? Sydney.
What, sorry?
I'm just trying to help the class get a little more alive. That's the reason I'm calling it. When it's almost dead, I try to. Alright, I want the reflected power density. What would it be? It would be going in that direction, but what would it be? P amp reflected. It's going to be 1/2. You give me that? Then what? Times magnitude of reflection coefficient times E naught incident. And you could put a number there, divided by. Your voice has changed. Alright, y'all with me on that class? What?
I thought you were asking anyone.
No, I'm just kidding. I was trying to put her in a spot. Now, I know these people, so I'm not trying to go around.
See though, if we're like given the initial, the H field initial, the H field reflected is
You're ahead of me. Yeah, that's right, that's exactly. Now, he just is usually ahead of me on everything. But here's the type of problem that could come at you. Instead of giving you the incident field, either H or E, what I might give you is the transmitted power density. Hint, what I might give you is the transmitted power density. So then I would ask you to work backwards and get all these things, all right? So don't panic when you, remember, you should be able to work a problem in reverse or forwards. If I give you any bit of information, you should be able to get the rest of it. Do y'all follow me on that class? So if I give you either power density, H field, or E field, either transmitted, incident, or reflected, you should be able to get all the rest. Yes?
the transmitted power density plus the reflected power density equal the incident power density?
Well, the way to say it is the incident power density minus the reflected power density will be the transmitted. So incident minus reflected is transmitted. I think you said it right. Okay, now wave guide. So help me out here. If I have a typical waveguide, and I'm not even going to draw this, I'm going to say this is a waveguide here, and it's got some cross-sectional dimensions, A and B. Now, be careful on this one. And I'm going to have a load here, ZL. Alright? And then I'm going to go ahead over here, and I'm going to put a source on it. Let me just put a straight-up voltage source with no resistance here. So I've got some VS here. And make this thing have a length L. Alright? I give you the cross-sectional dimensions. It's filled with air. And now I'm going to ask a few things about this. I'm going to ask you the voltage here. And I'm going to ask you the power dissipated by the load. Alright? So how do you remember this one? I gave you a problem on this. I gave you a couple problems on this. I gave you a quiz on this. Okay. So how do you do that? Well, probably the key thing to remember is you're going to have to get the characteristic impedance of that guide, right? And that means you have to figure out first the cutoff frequencies. And really, cutoff frequencies for the MN mode are what? Well, it's technically 1/2 square root of mu epsilon. We usually write that as just C/2, right? And then it's going to be times what? Square root of N, that's right, plus N over B squared, correct? Those are the cutoff frequencies for the different modes. The first thing we want to see if anything propagates. So we get the FC10 mode. Right? And that's what we want. 1 It's really, if you look at this, it's C over two, right? If it's free space. Maybe I shouldn't do that. It's for mu epsilon here. 1 over that, and then it's just divided by A. Y'all with me? That's the 1O mode. Then the 2O mode usually comes. Usually A is at least 2B, or B is less than B, 1/2 A. Either way, it's the long dimension. Y'all follow me? So these are usually the way the modes develop. You find out what that is, that's just twice the F1O mode. And then you find the next mode, right? Because it could be the 1-1, or it could be the O1 mode, pardon, the O1 mode. Y'all follow me on this one, class? So you can do this and you figure out what the lowest modes are. And hopefully, this frequency F0 lies between the 1O and the 2O mode. Because if it's below the 1O mode, nothing propagates. Y'all follow me on that? And if it's above the 2O, then you get two modes, and then you have power splitting in the different modes and going at different velocities. So here's a tip. I'm going to give you the 1O mode, the TE1O mode. Now I might ask what the next mode is and stuff like that, but I'm not going to. For the entire problem, that's what I'm going to ask you about. So when I get this, and I know what this is, right? You got the 1O. My next step is what? I call it K. And K is what? The square root of 1 minus, and it's really F, what? C over 1O, comma O, right? Over F squared, right? And that value K is going to be less than or equal to 1. Hopefully less than 1. If it's negative, you did something wrong. If you get a minus J there, what you did is probably flip the FC and F. You probably messed that up. And it is squared. A lot of people messed that up. They forgot the squaring in that quiz. I remember that. Everybody with me on this? Okay. Give me another minute or two. Just hang on. So once I get the value of K, now I get the value of the impedance, right? And if it is a TE mode, then it's going to be what? The waveguide impedance. I'll make it air so it's just 8 0, right? Over K ohms, right? It's going to be greater than 125, greater than 377. Y'all follow me on that? Once I have that impedance, then what do? Then I come here and I get the input impedance, don't I? Yep.
Do you need to find input impedance if you don't have a source resistance?
You sure do. Why? Because we have to remember the voltage that jumps right here is going to be equal to the forward going and the negative going. Remember? Yeah. And so we have to get that V0 plus. That's what I'm driving at now. Just give me a second to finish this thought. All right. I didn't have a chance to get through radar and freeze, but that was a more recent thing we did. You guys should be all right there. So if you look at this, now I know once I get, actually, let me do it this way. At this point, what we can do is say this Vs has some magnitude. And I can come and erase this. You're right about one thing. You're absolutely right. That Zn is not going to affect the voltage that jumps as it would. If I had a resistor here, then I'd have to do resistor division to get the actual voltage. But since I didn't put that there, I'll just finish the problem. So now I come in and I say that my Vs will be equal to V0 plus, and it will be times e to the j beta L. It will be positive here because normally it's minus, but that L length is minus, the z is equal to minus L. And then it's going to be plus the reflection coefficient at the load, e to the minus j beta L. You know how to get the reflection coefficient at the load, so you get V0 plus equal to Vs over this. Now, once you have this, how do I get the voltage at the load? Y'all remember this equation right here, class? The voltage at the load is when what? This L value goes to 0, correct, class? So then I can say, finally, voltage at the load for this one would be V0 plus times 1 plus the reflection coefficient at the load, correct? After I have that, I've got the voltage at the load. How do I get the power at the load? Well, if it was resistive, it would just be 1/2, right, times the voltage at the load squared divided or divided by the actual impedance of the load. Do you all agree with that? That's if it's pure resistive. If it's not, you can calculate the current, right? And you can calculate the current by taking V load divided by Z load, and then saying it's 1/2 the current squared times the real part of load impedance. Do y'all follow me on that? Or you can take 1/2 the real part of voltage times I conjugate. But remember, it's only the real part of the impedance that dissipates power. And I would definitely also, I didn't have time to do this, but I'd put a Z input right there, a Z source, just so you know how to do the whole problem, including that. But that only changes the value. Then you need the input impedance to get the value of the voltage at the input there. It's not giving us VS. All right. One last thing I'll tell you. We're in this room, so if it goes a little over, I'm not going to yank papers out of your hand. But if you're going to come, you can bring coffee, but don't bring anything that goes crunch or makes crumbs or disrupts the class. And besides that, any questions before I leave you? I'm trying to be as honest as I can.
Fiber optic, will it be in a slab?
No, slab wave guide. You're worried about, no, I'm not going to do that. I mean, we got a lot of material, all right? So I'm going to focus on the majors. Now, there possibly be some EMC, radar, freeze, and this stuff, but I can ask a whole lot of different things that cover different concepts. With one problem, just ask different things about it. And if you look at the homework and stuff like this and the quizzes, you got a good idea of what's coming. Yeah?
Are we looking at like 4 to 5 problems?
Probably 4 problems, but with multiple parts. I mean, if you've had me before, John, you know that I usually give 4 problems for a 50-minute exam, and there'll be multiple parts of each problem that I'm asking. And I don't ask something ridiculous usually. It's just something that if you know your stuff, you kind of breeze through it, but if you don't, sometimes you really stumble around and get lost, and it takes forever. Okay, I'm going up to my office and need to see you. Yeah, tomorrow I teach from 9:30 to 10:45, and after that I'll be up there. I'll tell you how long.